hand out project 3. And the first part of project 3 is writing out what's called your GCC student ID polynomial. So I'm going to ask you to hand that in just so I can see it, bring it to class on Friday or Monday the latest. Because if you do that incorrectly, then the whole thing is messed up. So usually I just check it, and it literally takes less than a minute to write out. I might even have you do it on Wednesday. So that's the next to the last project. The last project is really like a review for the final. So this project here is like your last project that's on specific material. Okay, so I think everything's lined up for the rest of the semester. So let's take a look at today's preview activity. So the main thing today is we've looked at quadratic functions in this form. Ax squared plus bx plus c equals f of x. Now, this is called the general form, but another name for this is the polynomial form. Because remember, your polynomial functions are just a finite sum of terms, which means they're put together by addition and subtraction only. So if you look at this form, there's a bunch of terms here, 3 terms. Ax squared is one term, bx and c is the other. So the general form, or sometimes you'll hear me refer to it as in polynomial form. And today we're gonna move from this form to another form, and that's the form you've been working with in number 2 here. Okay, so this is where you have each individual term spelled out, and now we're going to look at a parabola that's in this form right here, which is a little different than the general form. And I wanted you to see the relationship between the parent function x squared and how through your transformations you could actually graph this. So your transformations say, what do your transformations say to do to this? It says, well, you're going to double all your output, all your y values. So you're going to multiply your y values by 2. So I'm going to do that first. I'm going to multiply all my y values by 2. That's the first transformation I'm going to do, because we always do our shapes first. Then it doesn't matter which of these horizontal shifts I do. So since I'm working on my y's, let's do this one. This is outside your function or post-operation as well. The only thing that's done before your function of squaring is the stuff right there in parentheses. So let's do these two together. So this says add 1, because it shifts everything to the right one, and this says subtract 3 from y. This one says add 1 to x. So let's add 1 to x and subtract 3 from y. And we'll do both of those at the same time. So add 1 to x is -2. Subtract 3 from 18 is 15. So I'm just going to go ahead and you can check what you've done with this. Oh, 1. Okay, so those are my new points based on the transformation. So let's graph those now. -2, 15, I can't because I don't have a big enough scale on my y-axis. So let's just start with -1, 5, 0, -1, 1, -3. And now notice your symmetry kicks in. 2, -1, 3, 5. So now if we graph this new function, it looks like this. So where did the vertex of our new parabola end up? What are the coordinates of the vertex of our new parabola here? 1, -3. So if we think about it, if we go back to our original parent function right here at 0, 0 was our original vertex for our parent function. So what happened? It moved to the right 1, shifted right 1, and down 3. That's our new vertex after we've performed those transformations. So you see, now that we know transformations, we can look at any function and go from the parent function to the new function without having to graph the whole thing. Literally just take 4 or 5 points from our original function, move them to the right one and down 3. That's all we did. So here's really like the main part of what we're going to look at today. If we just had this function right here, now that you've done all the hard work of graphing and everything, if we just had this function, let's see if we can do some shortcut work. We know that the new parabola, the new vertex is this. Can we look at this function and identify, just from looking at the equation of the function, where the new vertex is? Anybody able to kind of scope that out, Eva? Okay, so the shape transformations aren't applying here, right? It's just changing the shape. So she's saying you just do the shifts. So where are the shifts when you look at this? All right, the x minus 1 and the negative 3. So listen to how Josh said that. He said the x minus 1 and the negative 3. That's where this shifts, right? So if you look at remember, let's look at the vertical shift first, because that always acts like we think. So the vertical shift is your y value. And the negative 3 there, when you see subtract 3, but remember, that's the same as add negative 3. So the sign of the operation comes along with the actual value, the y value, you see? Now, when you look inside, we remember that we don't call this a negative 1. We don't look at this and call that a negative 1. So when you look in here, you say, oh yeah, that's to the right one, that's adding 1. And notice how the signs here of the vertex either look the same or the opposite of what you see inside. The other way to think about this is, what value must x be to make that a 0, to go back to where it was? And x would have to be a 1 there, not a negative 1. So you can tell from looking at this particular form what the vertex coordinates are, which is a really cool thing to know for your parabola. That's kind of like, if you know where your vertex is, then you have a sense of how to graph it from there. So this form of a parabola is important because we can get the vertex directly from the equation. Okay, we can tell the coordinates of the vertex directly. I just for a minute want to put up I want to write out what the coordinates of this, or what this function's equation would be if we multiplied it all out and put it in polynomial form, a general form. So if we took this function g of x and we multiplied it out, so we want to put it in what's called the general form. I like to call it polynomial as well. So we want it to look like this: g of x equals ax squared plus bx plus c. So to do that, we have to square this, double it, and then subtract 3. So when I square x minus 1 square, I get x squared minus 2x plus 1. I double everything, 2x squared minus 4x plus 2, then take away the 3, 2x squared minus 4x minus 1. So this parabola could be given to us in 2 different forms. And you see that these 2 different forms give you very different information. This form, again, you can pluck off the vertex right away. This form, the only thing you can pluck off right away is you know something about the fact that the parabola is opened upward because this number is positive. And you can, if I cover up the 2x squared minus 4x, there is your y-intercept. That's like all you can tell so far. Right? But the other thing I wanted to point out is, look at this number out here. And look at this first leading coefficient right there for your x squared. Notice they're the same, and they will always be the same, because this form will always have 1x, either take away a number or x plus a number. And this number on the outside is always going to be, you can see here, even after you square that out, everything in there is going to be multiplied by this number. So these always stay the same. That particular number stays the same no matter what form you're using. Okay, so we're going to play around a lot with this idea today. All right, so let's take a look at the demo. And this is where your new language comes in. So now, again, remember the general form of polynomial form looks like ax squared plus bx plus c. Now we have what the book calls, and several books call it this. It's interesting. I've looked through several books. The standard form of a quadratic function. So you can get sort of all mixed up in the language. So the standard form. I don't know why they call it the standard form. I really like to think of this as the vertex form. Why do you think I like to think of this as the vertex form? The one like the one we just looked at. So the one we just looked at looked like this, x minus 1 squared minus 3. Why do you think I like to call this the vertex form instead of the standard form? I can pluck the vertex right out of it, right? So here it is written generally for any parabola. This is a very specific parabola we looked at, 2 times the quantity x minus 1 squared equals 3. So if we wanted to talk about this general quadratic right here, what transformations from the graph of our parent function does this form represent? So let's just look at this form and keep it general for a minute. Which of these constants, h, a, or k, affect the shape of the transformations? Which one of these constants affect the shape? A. Okay, so now I'm going to turn off Eva, so she can't contribute for a few minutes. Okay, so she answered A. Does everybody agree with A changes the shape? It's a multiplication outside of everything. So how does it change the shape? What does it do? Which way? Right, so it's a vertical shape change, right? That's all I want for now, a vertical shape change. All right. So which of these constants affect the shift transformations? Which of these constants affect the shift transformations? K is one of them, yeah, and H, yep. H and K. And how? How does H affect the shift? Horizontally. So H is a horizontal shift, and that means K is the vertical shift. All right. So what I'm going to do is I wrote a little GeoGebra demo for you. Watch how changing the values of A, H, and K affects the transformation of the parent function f of x equals x squared. So let me get up my little GeoGebra demo. This is kind of cool. This is so easy to do on GeoGebra. It's unbelievable. So notice this is your parent function x squared. And what do I have over here? I have a slider. So I can affect the value of A to change the shape of this. I can slide the value of H, which is your horizontal shift, and then I can slide the value of K. So what we're going to be looking at now is what happens to our parent function when we change these 3 constants. Okay, so I just want you right now on here, as we go through it, write down any observations that you see. Okay, so let's play with the shape change first. So right now, my shape change is 1 because it's 1x squared. So let's see what happens as I make this value bigger and bigger. I only have it go from -5 to 5. So as I go from bigger to bigger. So you want to see now, that's A being greater than 1, and now A is being less than 1. So what's happening to the parabola? So you might want to write down that observation. However you want to say it. Okay, I'm just going to go back to 1 now. Write down that observation. Now I'm going to play around with h, which is this term inside the function, inside the operation, pre-operation. It's affecting the input. It's a horizontal effect. So h is positive. H is negative. So now when h is negative, notice it moves to the left because subtracting a negative puts the plus in there. So it still works just like our transformations work. So that shifts it horizontally. And now we got our vertical. K is positive, it goes the way we think. K is negative, it goes the way we think, vertically up and down the axis. Let's get everything back to 0 for H and K. Bless you. And now let's see what we can say more generally now in the box that we've played with that. So what can we tell about a parabola when we look at this standard form or the vertex form? The standard form is convenient because it immediately identifies the vertex of the parabola, h comma k. So it is always in this form to pick out h, x take away h. So when h is a negative number, it will look like x plus h. But if k is positive, it's going to appear to be a positive. If k is negative, it's going to appear to be negative. So that's what I'm saying here. Note, in this form, h has opposing sign and k has the same sign. Okay. The leading coefficient is called a. That's what we call this variable, this constant leading coefficient. And what did we just notice? That when a was positive, the parabola opened upward. Yep. And when a was negative, it opened downward. So that's one of the things a will always tell you. And based on the absolute value of a, the bigger a is, then the more narrow this becomes. So larger values of the absolute value of a make the parabola taller, whereas smaller values of the absolute value of a make it shorter. So remember, we called this taller bit, it was stretched, and this compresses it or shrinks it. So if we wanted to make an accurate sketch of this parabola, once we find h and k, and once we realize whether it's opening or closing, the next thing to do would to be able to find your x and y intercepts. All right, I want to go back to the preview activities because I realized I didn't answer this next question here because I was writing in here. So the next question in the preview activity said, what was the role of the vertical line x equals, let me get a different pen color here, x equals 0, which is this line right here. What is the role of this in our parent function, and what is the role of x equals 1 in our transform function? So what role does each of these two vertical lines play in terms of the parabola? They split it. What do you mean by splitting? They run through the vertex, the x value of the vertex. So the x value of the vertex, whatever your x value is of your vertex, is the equation of that line. And when he says it splits it right in half, it means that's your line of symmetry. So every parabola will have a line of symmetry. And that's why I asked you the same question on your test as I did on quiz 2. All functions f of x equals x squared are even. Well, here's a function all transformations of x squared are even. Well, here's the transformation of x squared. This isn't an even function because it doesn't fold over the y-axis. So any horizontal shift of this parent function is going to not make that even. All right, so we've got these ideas now, and we want to put them all together. We've got the vertex. We want to know a little bit about how to deal with the x and y intercepts and this line of symmetry. So what does a graph of a quadratic function look like as the leading coefficient gets closer and closer to zero? So regardless of what form you have, as this number right here gets closer and closer to zero, what happens to the parabola? Whether you have it in this form or imagine it in this form. It's shrinking, yes. It's definitely shrinking. It's getting closer and closer to the x-axis. So here I am, whether I'm a happy parabola or a sad parabola, and then think about my arms coming down like this. A's getting smaller and smaller and smaller. What am I starting to approach? The x-axis, and what type of a line? Right. So let's take a look at that again. So let's see what happens as A gets closer and closer to zero. We can look at it right here. So here we go. A is now 0.35. We're getting wider and wider and wider. Ooh. So there I am at zero. Zero, I'm just bx plus c, right? So as you're close to zero, you get very close to being a straight line. We know that if A is zero, we don't have a parabola anymore. We have a linear function. So as we get closer and closer to zero, the graph gets closer and closer to becoming a line. That's just one of those kind of conceptual thought questions. All right, here we go. How do we change forms now? How do we go from this polynomial or general form, ax squared plus bx plus c, to this standard form or the vertex form? Because here I can look at this and say, oh, I know what the vertex is. When I have it in this form, ax squared plus bx plus c, I don't know what the vertex is. Well, the good news is that there's a formula to find the vertex if it's in this form. Again, I want to point out what I pointed out earlier. The value of A in both forms are exactly the same. So if I give you a parabola in the general form like this, or the polynomial form, and you want to put it into this standard form here, you pluck off A, the leading coefficient of your x squared term, and you put it right in there for this A. That's why we use exactly the same constant for both of them, because they are the same. Eva? That's right. So let's take a look at the formula, and you'll be using this over and over again. If you have a quadratic equation in this form right here, how you're used to seeing your quadratic equation, then you can find the x value of the vertex, which we call h. That's the x value of your vertex. H is the x value, by taking the value of b, taking its opposite, and dividing it by 2a. That will always give you the x value of your vertex. It also will give you the equation for your line of symmetry, because your line of symmetry goes right through the vertex, right? Then how do you find the y value, or k? You just plug it back into your equation. So you just find f of the opposite of b over 2a. So this should look very familiar to you. Does anybody recognize where that might come from? Nobody recognizes that? Eva? Squaring a binomial. Let's see, if I square a binomial with the negative b over 2a, come on. I don't know, I'd have to think about it a little more. Yeah, yeah. I don't, okay, that would be twice the middle term, right? Nobody recognizes the opposite of b over 2a from anything we've looked at? I think it's because we didn't sing this semester because I had a cold. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Look at that right there. It's right there in your quadratic. Because remember, this breaks up to look like this, the opposite of b over 2a, because remember, that denominator goes with both of the terms on top. So you can separate this so it looks like this. So notice what this says. This gives you the two x-intercepts of your quadratic. So let's pick a really easy quadratic to look at for a minute. Let's look at this. F of x equals x, say, minus 2 and x plus 2, something nice like that. Well, I should make it so that it doesn't have, there we go. So if you were solving this for 0, right, this quadratic equation for 0, you would have an x-intercept at 2, 0, because 1, 0 is x equals 2. That makes that 0. And your other 0 is negative 4. So if you were graphing this, you would say, okay, and you would have been given this function in this form originally. If I use FOIL now on this, I get x squared plus 2x minus 8. So you would have been given that form, and I would have asked you to solve this quadratic equation. Right? And you would have set it equal to 0, you would have factored it, and you would have come up with these two answers. And we know that on our graph, those two answers look like this. They convert to being this. We know since our leading coefficient here is 1, right? There's a 1 out there. That's the same number as there. So this is just opening up with the same shape as x squared, no stretching or compressing. And where does the vertex come in? Where am I going to find the idea of this being split in half? Is the language that Jasper used. The line of symmetry is going to split this in half. So where must the x value be in relationship to those two x values where I'm going to split it in half? Where must it be between these 2 points? Now, how did you get negative 1? It's halfway in between, right? All right, so if we put a line down through negative 1, folks, that is 3 units to the left of 2, 0, and it's 3 units to the right of negative 4. So you know that this parabola is going to come down, it's going to go through negative 4, 0, it's going to come down here somewhere, we don't know exactly where, and at negative 1, it's going to turn around and come back up through 2, 0. So we know that x equals negative 1 is the line of symmetry. It's also the point, the x value, that when you add 3 to it, you get out to that x-intercept, and when you subtract 3 from it, you get to that x-intercept. Well, folks, look at this. X equals, so here's our original equation right here, negative 2 over 2a plus or minus negative 2 squared minus 4 times a times c all over 2a. What's this number right here? Negative 1. That's your x value of your vertex. There it is, right there, negative 1. Now this says you start at negative 1, and to get one of your x-intercepts, you're going to add 3, and to get your other x-intercept, you're going to subtract 3. And let's see what this comes out to be. It better come out to be plus and minus 3. Because that's where your x value of your vertex always will be. Okay, so what's this? 4 take away 32, which take away a negative 32, which is a positive 32, which is 36, and there we go. Plus and minus 3. So the formula for the vertex, should you ever forget, try to remember what the role of the vertex is, okay? Now, you won't forget because you can always take notes, cheat sheets, and you'll have take-home stuff, right? But I want you to just get a physical sense of why the equation is negative, the opposite of b over 2a. Because this thing always tells you, start at my vertex, add some number to get to one of my real zeros, and subtract another number. Now, clearly, if your parabola is sitting up in the air, hanging down below the x-axis and doesn't have any x-intercepts, that's when you get the I business going on in here. That's when you get your complex solutions. All right, it's probably more than you needed to know, but I can't help it. Every time I see that negative b over 2a, I want you to see the relationship between your quadratic formula, the vertex, and how it all fits together. All right, so here's the type of thing you're going to be doing for homework. Graph the quadratic equation. Notice what form it's in. It's in your standard form, how you're used to seeing it. It's a bunch of terms here. -1 times x squared plus 4x plus 1. And we want to put it in this standard form or the vertex form. And then we want to graph it. So these would be the series of steps you would go through. I've just kind of laid them all out here for you. You go through these steps, you can graph any quadratic function. So notice I've left A as a blank, H as a blank, and K as a blank. So that's what we need to fill in. So which of these three constant values can I put in right now without doing any work at all? Just from observing this function, which of these three blanks do I know? All right, I hear K. Now, I hear A. And I thought I heard an X, but okay. So K, remember, is the Y value of the vertex. And see how it comes outside of this form? So the K the +1 that's here is not the same as the plus K that's here. Okay, this is C. If we go back and write this in the general form, it looks like this. Now, if we were lucky enough that this value was always the same as this, then we would have called this plus K. So you could have gone right from this form over to here. So that's one thing that people look at. When you put a 0 in this form, you can get your y-intercept right away. Okay? But that C value is not the same as K. C does not equal K. And I'm glad someone said that because that's something that students often think. And it's not the situation here because these are different forms. But do you see in the same letter from one form to the other? The same exact letter? Anywhere? Lyndon? Do you see? You see A? Yes. We know what A is. It's -1. A is -1 in this form, and guess what? A is -1 in its other form. So right away, you can put a -1 out front there. And what does that tell you? That this parabola is going to be a sad parabola. It's looking downward, and it has the same shape as x squared. So A equals -1, and it opens downward. So when I come down here, I can just go like this. I know how this parabola is going to end up. Sad. Pointing down. Notice with parabolas, your your arms, if you want to call these the arms of the parabola, always go in the same direction, whether they're both up or both down. So that's going to change on Wednesday for other equations. Okay. Next, we need to find the vertex. So we can't pluck it out because it's not in the vertex form. So let's use this beautiful new formula we just talked about. To find the x value of my vertex, which is called h, I take the opposite of b and I divide by 2a. So up here, I want to identify a, b, and c. A is -1, b is 4, and c is 1. So the opposite of b is -4 over 2 times -1 is -4 over -2, which is 2. So now I can come inside here and fill in the 2. That's my h value. X take away 2 squared. Okay. Are we done? Can we start graphing this and getting x and y intercepts? Do we have our full equation? What do we need now? K, which is the y value of your vertex. And to get K, you just plug the X in, you find F of 2, F of 2. So everywhere you see an X in this original formula, negative 2 squared plus 4 times 2 plus 1. So that's the opposite of 2 squared is negative 4 plus 8 plus 1, which is positive 4 plus 1, which is 5. So now I know my vertex is 2, 5. So anytime you have an x value to get the output of your function, you just plug it into your function. You've been doing that forever. So that's not anything new. It's just something you have to remember how to get your y value. Now we're ready to graph the function in standard form. So let's rewrite f of x in standard form. What's it going to look like? Well, negative 1 is a. X take away 2 is the value of h. We square it and we add 5. So this is now the vertex form or our standard form. No, that's how to get the h, Dylan. So now I know that x is 2, and when x is 2, I want to find out its partner y. So to do that, Dylan, I just put 2 in for x and find y. Negative b over 2a is for the x value to find h. That's the x value of your vertex. Okay, so you just plug it back. Once you find the x value, you know the x value of your vertex, and you just plug it right back into your function that's given to you to find the y value. All right, so now look, we've got two forms of the same parabola. So right now, I can go down and put in 2, 5 from my vertex. Right? I can come down here and I can say, okay, 2, 5. Right here is going to be my vertex. Is this vertex going to be, is this 5 right here going to be a maximum value of my function? Maximum or minimum value of my function? And how do you know it's max, Josh? Right. So since this graph goes down, we know that's the highest value. 5 is the maximum value. Yep, 5. There's not going to be any other y value bigger than 5 in this whole infinite number of points. So we know something about this. We don't know yet where this is, where this is going through, but we know it's going to do something like that. That's all we know right now. Okay? We're going to get more information in just a minute. We know the vertex, we know that it opens downward, and we also know the equation of the line of symmetry. We come right down like this. Here's my line of symmetry, right down through the vertex. So my line of symmetry is x equals h, which is 2. It's the h, it's the x value of your vertex. All right. So what else do we need to graph a parabola? There's a couple of key points here. Let's find them. The equation for the line of symmetry we just did, x equals 2. And now how about the y-intercept? Well, the y-intercept is plugging in 0, x equals 0. So my equation will look like this. 0 take away 2 squared plus 5. So you see, John, right here in this form, the 5 is not the same as the original y-intercept. So if you do all that work, you get, we know that it's 0, 1 from the original form, but, let's just play this out. Equals 1. So 0, 1 is our y-intercept. So we go to 0, 1. So now we know where it's going to go through the y axis. Okay. So we still need the x-intercepts, and here's the key idea. Remember, this vertex now, I didn't do a very nice line of symmetry, did I? I got to erase that line of symmetry. That really bothers me. Okay. So I want to make a solid line straight down through here. 0, 1. So look, here I am at x equals 2. That's my line of symmetry. Here is my y-intercept. It's 2 units to the left, right? 2 units to the left. So it must have, at the exact same height, another point 2 units to the right because of the symmetry of this. So you can find the point that's symmetric to your y-intercept by just moving the same number of points, same distance, 2 units to the right, and you're at 1 still. So 4, 1 is the point that's symmetric to that y-intercept. So once you find your y-intercept, you can always find its partner in crime, which is on the other side of your vertex, the same distance away at the same height. So our y-intercept is 0, 1. The point symmetric to the y-intercept is 4, 1. Okay, so we've got the vertex, we've got the line of symmetry, we've got the y-intercept, one other point, and now all we have to do is find the x-intercepts. How do you find the x-intercepts? Y equals 0, right? So we put this like this, x minus 2 squared plus 5. So let's do this, instead of multiplying this all out, let's do it the quicker way. Subtract, we want to solve for x, so subtract 5 from both sides. Negative 5 equals negative 1 times x minus 2 quantity squared. Now, divide both sides by negative 1. 5 equals the quantity x minus 2 squared. You got something square equals a constant, so you want to extract the roots by finding the square roots of both sides. Plus or minus 5 equals x minus 2. And now add 2 to both sides. And there are your 2 x-intercepts. Those are exactly the 2 exact zeros of your function. 2 plus the square root of 5 and negative 2 minus the square root of 5. These are the zeros, the values of your zeros, which means those are the values of your x-intercepts. Those 2 are the values of your x-intercepts. So all we can do now is estimate them, so we can put their spot in here on the x-axis. So let's estimate these. These are the exact zeros, exactly the solutions to this equation. So let's go to our handy dandy calculator and get an estimate. So we can plot it. 2 take away the square root of 5 is negative 0.236. So I'm going to say, okay, 1x is approximately negative 0.24. And what's the other zero approximately? 2 plus the square root of 5. 4.24. 4.24. So all you do now is you just say, okay, best I can do is estimate it. So I'm going to say there's negative 0.24 and here's positive 4.24. And then you just come down, boom, boing, and you're done with the sound effects. Boing, boing. So how did we do this? We first found out whether it opens up or down. We then found the vertex. We then found the y-intercept, the point on the other side of the line of symmetry that's equidistant away. It's symmetric to the y-intercept. Your 2 x-intercepts, voila, you're done. So you have a little bit of time to work on your class activities. There is one more question. Finally, how would you change the function back to polynomial form? You would square this, multiply everything by -1, and then add 5. Okay, you would just do what this says to do. Okay, square it, x squared minus 4x plus 4, then everything gets multiplied through by -1, and you add 5. Okay. Oh, I forgot we have one more question. Sorry. So far, we've figured out how to draw the graph from the equation. How do you go backwards? So here's the equation. Here's a graph. How would you get the two forms that we just looked at from the equation? Let me remind you of something. You have done this before, and you will do it a million times more. Every time you find the slope of 2 points on a line and you've got to find that b value for y equals mx plus b, what do? You pick a point off your line and you plug it in. Same idea works over and over and over for every polynomial function, every exponential function. You can do this over and over again. So what form do you want to use here? What is going to be the easiest form, do you think, from looking at these points? Standard, which is the vertex form, right? So y. You already have the vertex, right? Perfect, Lyndon. Right there, you know your h and k value. Holy schmoly. I can just put that right in right now. I'm almost done. X take away 3 plus 5. And guess what students always forget to do? Put the square in. I'm telling you, it happens every year. So make a little note. Don't forget your square. We are actually looking at parabolas there, right? It happens. I know. It's terrible. It's awful. How many points? Everything. You're not graphing a line. I don't know. Depends on my mood, I guess. All right. So what do you need to find, folks? What's the only thing left to find? A. Do you know if A is positive or negative? Happy parabola. Arms are up. So we know A is a positive number. How are we going to find A? If I know an X value and its corresponding output value, I can solve this equation for A. Do I know any X, Y point that falls on this parabola other than the vertex? Yeah, I know 2 of them. Why not pick the 0? It's really easy. 0, 23. So let's plug in 0, 23. So 23 is equal to f of 0. 23 is the partner of 0 in this function. So 23 equals a times 0 minus 3 squared plus 5. I just put the 0 in for my x and the 23 in for my y. And now I have all the information to solve this equation for A. And I've got everything I possibly need. 23 equals A times 0 take away 3 is -3. When I square it, I get a 9 plus 5. So to solve this equation, I know how to do this long before I came into this class. It's just a baby linear equation to solve. 18 equals 9a, a equals 2. So now I have all the information I need. Here is my function. 2 times the quantity x minus 3 squared plus k. My vertex is right here. Oops, plus 5, sorry. Right. And then to put it back in the other form, I square it. X squared minus 6x plus 9. 2x squared minus 12x plus 18 plus 5. 2x squared minus 12x plus 23. So you can see the A values are exactly the same in both forms. This is your general form. This is your standard form. Whoops, this is your standard form. You can go from one to the other. They both give you different information. Okay, now you're ready to start your class activity. Okay.